So we get started. Hello, everybody. Thank you for coming. Like I said, I appreciate everybody coming. I know that Kevlin is a very interesting speaker, and he and I are up against each other again. But anyway, my name is Marshall Clow. I work at Qualcomm in San Diego, and this talk is called The Detection Idiom, A Better Way to SFINAE. So we'll start with a bit about what I do. I work at Qualcomm. You might have heard of us somewhere. We do something with cell phones. I forget what. But now I work on libc++, which is a C++ standard library implementation for the LVM project. I also work on the standards committee in the library working group. And so those two jobs kind of dovetail pretty nicely. As changes get made to the library portions of the standard, I have to go implement them. In this talk, I'm going to show you a lot of code. All of this code worked once before I put it on my slides and started editing to make it fit. So there may be minor typos there, but it worked once, okay? Also, if you have questions along the way, please don't save them up till the end of the talk. Just put your hand up and I'll point at you and ask the question right then when it's fresh in your mind. There's a faint chance that I will decline to answer the question right away and say, just hang on to it because I have a slide coming up for that. But in general, I'll try to answer it pretty much immediately. Also, in spite of the title of the talk, due to space reasons on the slides, I'm probably not going to show a lot of actual uses of SFINAE, but tools to help you do SFINAE, and I'll just static assert things instead. So you can see that these things actually, these conditions are held at compile time, and you can use them in a SFINAE context to control how things get built. Also, this talk will be full of terms like SFINAE and overload resolution and template metaprogramming. I'm not trying to scare anybody away, but if you're not familiar with those terms, I haven't done at least a little of it, you're liable to get lost at some point here, and I apologize in advance. Any questions before we get started? All right, let's see if my clicker works. The detection idiom. We're going to go through several sections here in the talk. We're going to talk about what it is, what problems does it solve, what does it look like, how does it work, how do I use it? And I have a bunch of examples, and we'll work through the examples in detail. But basically, anyway, what is it? What is it? It's a collection of classes, not very many actually, but it was introduced in the Library Fundamentals TS2. It's still there. It was produced mostly by Walter Brown. Anyway, it's very, very sparsely mentioned in the Library Fundamentals TS. There's, in the header for the experimental type traits, the synopsis for the experimental type traits header, it's listed there. And in the text of the TS, there's a chunk of code and a couple examples, and that's it. There's no words there. There's no description of what it is. There's no description of how you would use it, why you would use it, why is it important, any of that stuff. There's just some code there. Most of the times, if you see something in the standard, there's at least a textual description of it. People on the committee like to say the standard is not a tutorial, and it's not. It's a specification of things. But usually there is like, a vector is a sequence container that provides contiguous storage of, blah, 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 or, allocator traits provide, a unified interface to different allocator types, or no, there's none of that here. There's none of that in the detection idiom. There's a section called Metadetect that has no words in it, just code. Yeah, and it includes two structures, void t and none such. None such at least has an interesting name. Void t is a very odd name. It includes an exposition-only type called detector. And then it includes a couple of type trait-like structures is detected, it is detected-T, and a couple of variations of them, and that's it. And it's like this kind of appeared, it's just kind of put there in the middle with no hints at all. And yet it's amazingly useful. So, but where did it come from? It came from Walter. Walter Brown has been on the C++ committee for a long time. He is retired from Fermi National Lab a few years ago. A very nice man, very smart man. And he did this as part of, he came up with this as part of research on other parts of the standard library. He was looking for, trying to implement SFINAE-friendly alligator traits and iterator traits and common type and things like that. And he kind of nosed around on this idea for a while. He wrote it up in three papers, and gave a couple talks on template metaprogramming at CPPCon in 2014. At the end of the slide deck, I have links to the CPPCon talks. And those mention void T as one of many techniques, void T and what grew into the detection idiom. But still, it's one of these things that not a lot of people know about. People who have implemented the library fundamentals TS, sometimes they just, they put it in there, they follow the code that's in the library fundamentals and don't use it for anything. But once you realize what it does, if it matches up well with the kind of problems that you're trying to solve, then this is a great tool. And so the reason I proposed this talk was because I thought a lot of people would like to know about it. So, question is, what problem does it solve? So when you're building up, when you're writing templated code, sometimes you have to actually provide alternate implementations or alternate strategies depending on the types or some characteristics of the problem you're trying to solve. You just solve, I mean, the classic one of these is in vector when you do a pushback and you have to reallocate. There are three, every standard library has three different strategies for dealing with moving stuff to the new memory, right? If it's a trivial type, you can just memcopy them and you'd be done. If it's a movable type, in particular if you can move it without worrying about whether an exception to be thrown, you can move the types, which is probably cheaper than copying. It's supposed to be cheaper than copying. And if neither of those are true, you have to actually copy, destruct. And you go through this dance to get your exception safety guarantees. There's a couple other places in libc++ where we have three different implementation strategies depending on various things. What kind of iterators you're handed. Reversing a sequence, there's an algorithm called reverse, right? Reversing a sequence is actually a significant amount of work if all you have is forward iterators. Okay, but if you have bidirectional iterators, it's actually pretty easy. You have half thing at the end and a half thing at the beginning, and you swap a pair, and then you move in and you swap a pair, you move in and you swap a pair. And it's all real easy. And if you have it in a list, you don't even do any swaps, you just move pointers around. But in any case, so the way you usually do this is through that horrible acronym SFINAE, where you provide alternate representations and you arrange things so that when the compiler generates an overload set, it picks the one you want. Is everybody here relatively familiar with how that mechanism works? Do I need to explain that, or shall we move on? If you're not, it's okay. Okay, so do people want me to explain building of overload sets and resolving them? Or is everybody familiar with that? If you're not familiar with that, raise your hand and let me see. I see a couple. Okay, so what we'll do is we'll give it basically a 2-minute description. So every time you invoke a template or make a function call or something like that in C++, what the compiler does is it looks around, it has a name. And it says, I need to figure out what I'm going to do with this. Probably the easiest easiest thing to deal with this is the stream insertion operator. You know, you say standard cout, left angle bracket, 3, semicolon, okay? The compiler says, I'm looking for an operator, angle bracket, that takes an O stream and something, and I have an int. And it builds a list of all of those operators that it knows about. And this is called building an overload set, okay? And there are tens of them, at least, in the standard library. And user programs can define more. There's stuff for strings, there's stuff for ints, there's stuff for complex, there's stuff for all sorts of things. I mean, seriously, there are tens of them. This is a major source of complexity. Compile time is resolving those actual, the double angle stream insertion operators. And what it does is it figures out what all these, builds this overload set of all of them, and it goes through each one and says, is this a valid one, right? Is this a valid one? Can I possibly use this in this context? And it looks and it says, I have an int, and I have this thing that takes a string. Is there any way? And surprisingly, yes, there's a constructor for string that takes an int, so it keeps that in the set. I have a long. I can convert the int to a long. Okay, it keeps that one. It goes through, it says, I have, I don't know, a file handle. It says, I can't convert it into a file handle. It drops that out of the overload set. It builds this overload set, okay? And some of these are regular functions, some of these are templated functions, some of these are whatever. And so it may try to instantiate various functions, templated functions. And this is where this horrible acronym comes in. If you try to instantiate this template with an int, and you get a compile error during the instantiation, the compiler says, oh, well, that's not a candidate, and drops it. And what that means, that's where SFINAE comes in, which stands for substitution failure is not an error. So it tried to instantiate this template with this particular type, and it said, nope, that didn't work. And rather than generating a hard error and aborting the compilation, it just removes that from the overload set that it's building. Now, eventually, it finishes building this overload set, and it has this list of possible things that it can call. If there are none, it says, I'm sorry, I don't know how to do operator angle bracket for int to an O stream, and gives you a compile error. If there's one of them, it says, I can do that one. If there's more than one, and frequently there is, it ranks them. And it ranks them according to a set of rules which are described in the standard. If the parameters are an exact match, that's a better match than something that involves an implicit conversion. So converting int from long to int to long, for example, will get ranked lower than something that would take the int directly. Okay? Non-templated functions are ranked higher than templated functions. Things that take ... the C-style varargs are ranked at the bottom of the list. Anyway, and it ranks them all. And then it takes the highest ranked one and says, that's the one I'm going to call. If there are two of them, more than one of them, I should say, that have the same ranking, then you get the error from the compiler. These two calls are ambiguous. I don't know which to do. And again, you get a compile error. So for every time you do one of these things, the compiler builds an overload set and then ranks all the things that are valid in that overload set and then picks the best one. And this happens all the time, and this is done, this is done pretty much everywhere. And so what SFINAE is a way of managing some of the entries in that overload set. You can, in fact, use SFINAE techniques, and in particular, there's a thing built into the standard library called enable if, which basically lets you say, I want this to be a candidate for this call if these conditions are true. Okay, and it does this by actually causing a compile error if the condition is not true, when the template is instantiated, which causes it to drop out of the overload set and not get considered. Okay, so That's what building an overload set is. That's what SFINAE is, very quickly. And the standard library provides a whole set of what are called type traits, things that are simple structs. People call them, sometimes they call them meta functions, but they're structs that provide you information about a type. You give it a type and it gives you some other information back. And people use this to build SFINAE constraints on their templates to do the right thing. And there are a whole bunch of them. Is a particular type default constructible, say? Is a particular type copy constructible? Is it no except move constructible? Is it a trivial type? There are probably 50 of these, okay? And is it an aggregate? Is it a function type? And so on. Anyway, there's a lot of them in the standard library. And if these things actually do what you need, you're golden. I mean, you use those, you pass them into enable if, and life is good. But they don't cover all possible eventualities because the people who write the standard are A, say, well, that's not a general purpose thing, and B, they're not omniscient. So the detection idiom is a way of basically saying, it's a way of easily generating more of these type traits, a general way of generating more of these type traits. But at the base, it's a way of saying, here's a chunk of code. If I try to instantiate this code with these types, is that well-formed or not? And getting an answer back at compile time rather than getting a compile error, which as a library writer is something you really want. You don't want to, you want to either be able to give your users a good error message, or you want to be able to do alternate implementations based on the capabilities of the type you get, rather than just dying, rather than having your users' programs fail to compile because, oops, I didn't think of that. And so we're going to be walking through some examples of how the detection idiom does this. I have to say that I spent a while in 2014 before I found out about this, trying to write a thing that basically I called is well formed, which turned out this does. I mean, there's a lot of places in the standard which says things like calls da-da-da-da-da if that is well formed, otherwise calls something else. Or, the expression ba 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 must be well formed. It's like, I had a trait in libc++. I had a chunk of code called is well formed that I knew I wanted, and I couldn't figure out how to write. I mean, I had something that worked kind of, but this is much better. Any questions so far? I mean, this is really the basis of void T and the detection idiom. Is this code well formed when I give it these types? Okay, simple example. Really, really simple example. I have two types, yes and no. I mean, I'm going to be using yes and no for the rest of this talk, okay? Yes and no. One of them has a nested type def called type. No does not. I want to know whether or not it has a type or not. And this is a very common thing. You can Google this. You look it on Stack Overflow. You can find several techniques how to do this, okay? But none of them are, in fact, this simple, okay? And this is the pattern that you'll be seeing a lot of. We define a type function that takes some number of types as parameters and defines a new type, okay? And then we use the mechanisms in the detection idiom to determine if that's valid. So in this case, right, we have this function, has type. All it does is it takes a type T and returns : type, the nested type def. Okay? And you can see how that would work for yes. If you pass in has type of yes, you would get void back. has type of no, well, it has no type member, and you would get a compiler. And that's really the question we're trying to ask. Is there a nested type def here? If I try to name no : type, do I get a compiler? Anyway, and so isDetected is one of the tools in the detection idiom that we'll talk about. And you can see here static assert value. Is detected? Yes. Is it not is detected? No. And both of these static asserts succeed. Yes. There is a is detected V. Yes. That was the question. Was is there an is detected V? Yes, there is. Anyway, and I use that in other places in this slide, but in this deck. Anyway, this is about as simple an example as I can get. You're testing to see if a type or some types has a nested type def type. Any questions about this? I mean, I haven't shown you how it works, so hopefully there aren't too many questions. Okay. All right, a slightly more practical example. This one actually got inspiration from looking at allocator traits. Allocator traits lets you reason about things about allocators. Allocators are quite loosely defined. There's very few requirements on allocators, but there are lots of things that people want to know about allocators. In this case, we have yes and no that have a thing called a size type. Okay, it's a nested type def, and it's supposedly some type you can use for numeric calculations having to do with this. And again, the detection function that we write is basically just names that type. In this case, we're using something slightly different. Instead of is detected, we're using detected or, where you could say, give me the thing that we pulled out of the type, or give me a default type. And so here I'm just saying, I need a variable of that type. That type, if it's not that type, I'll make do with a short. And this declares a variable and gives it a value, and then we can do calculations with it. Yes, Peter?
How do you know which argument has which meaning? Detect or T? Is there kind of easy memorizable?
Yeah, the first one's the default. But yeah, the first one, it's default metafunction args is the way it goes, and all the way through. Sorry, all the way through this. All right, other questions? Okay. Anyway, again, you can do this there are other ways to do this, right? You can write out a bunch of template metaprogramming yourself and get this equivalent functionality. But my contention is it doesn't get much simpler than this. You write a using, which basically says this is what I want to do, and then you feed it basically to the factory, and the factory applies it for you. Okay, so what does it look like? What is this thing here? All right, well, starts off, we have two structs I mentioned. We have void t and none such. And wow, they don't look like much. This is like, I looked at this and said, Walter, I can write this. This is easy. This doesn't do anything. Especially the second one, okay? The second one, none such. None such is this concept that actually I've looked through several standard libraries. Actually, all three of the major standard library implementations, they all have something like this. They call it various things. In libc++, we call it __NAT for not a type. And it basically is, something to return when you don't have anything to return. Okay? This is a really boring type. It has no members. It has no constructor. It has no destructor. It has no assignment operators. You can't do anything with it. You can't make anything with it. It's just like a marker. It's a type that can't, it's like void. It's a type that you can't instantiate. Void T, on the other hand, void T is kind of interesting. Void T looks kind of like one of these things here. It's a meta function. It's a function that takes as parameters any number of types and hands you back void. And you say, okay. So, so what? But that turns out to be really important, and I'll show you later, okay? Anyway, then, yes?
Why do you need none such? If you say it's pretty much the same as void, why can't you just do void, or is it something that comes later?
It's something that comes later. So, no problem. So the other thing that's in the description of library fundamentals is this exposition-only class called detector. Now, for those of you who don't read the standard library for fun, which I hope is most of you because it's not fun, exposition-only means is a way of describing behavior. The standard uses describing behavior without actually saying this thing exists. So if you go looking through your standard library sources, again, not a thing I would recommend for fun, but sometimes you have to go look and see what things people are doing. You won't find a struct named detector, okay? But you will find something like this, and it probably has some reserved names. It starts with a double underscore or something like that. But in the standard, this is used to describe behavior, okay? We basically pretend there's a struct like this, and we're going to define other things in terms of this. So what have we got here? Interestingly enough, this is unlike most type traits. Most type traits will either give it a type and it returns you another type, or you give it a type and it returns you some kind of value. Who can give me an example of a type trait that returns a value rather than a type? All right, is same, right? Yeah, I was thinking of like rank, which you give it an array type, it tells you how big the array is. But yeah, is same returns you a Boolean, right? Give you two types, it tells you if they're the same. A type that would return another type is, say, add const. You give it int, it hands you back constant. But anyway, right, I was actually thinking of non-Boolean things. There are rather few of those, but you're right, is same is exactly. Anyway, so there's two versions of this. One that the value is false type and the type is default, and the other one that the value is true type and the type is op. Remember I said the order was default, pretend that's not there, function, and arguments. And the reason you pretend that's not there is because you don't ever actually specify it. If you look at detector, it's default, ops, args, and this gets filled in for you. And we'll see that in the next slide. But so the way this works is, well, let's go on to the next slide because this is, again, we'll come back to this one. And these are the things that you actually use, okay? And they're defined in terms of the struct detector, which doesn't exist, okay? But the struct detector is there to provide behavior. So is detected, again, you have function, or you have, function void op args. So what do we do here? We say none such. Again, it's here as a placeholder, okay? Void op args, boom. And so is detected, what does this actually do here? It calls detector, and let's go back to detector now. Yeah. So when it tries to instantiate detector, and it looks, it has two of these. It says, huh, there's two different implementations of these. And so the compiler will attempt to instantiate them both, build an overload set, and then choose the best match. Now, this first one, always going to succeed instantiating. Okay? Is always going to succeed because and setting the nested type dev value t to be false. This one attempts to apply op, that template function that we talked about earlier. We go all the way back to here, in this case has size, to the arguments, okay, and wrap that in void t. Now, the reason you want to wrap it in void t is because void t will swallow the compile error if it fails to instantiate. And if this all succeeds, you get type be the result of that type function that you passed in, and the value is true, which means it's succeeded. And that's the guts of the whole thing right there. That is the guts of the whole thing. You take this type function and apply it, and it will tell you, did it succeed and what the result was. If, in fact, they both succeed to instantiate, this one is more specialized, and the compiler will pick it, rank it higher when building the overload set, and will pick it. And that right there, that is the guts of the detection idiom right there. You describe what you want to test, and say, apply this to a type or a series of types, and it comes back and tells you, yeah, that'll compile, or no, it won't. Yes?
How does the rank higher work? I would usually expect that something that doesn't work out is just blocked from the overall set, and
right.
Also just excluded.
So if the type function back here, if this type function fails to instantiate, okay, this second one will fail to instantiate, and obviously will not be included in the overload set, and you will have one thing in the overload set, which is this one. Yeah. If it succeeds, they'll both be included in the overload set, and this one will be more specialized because it's using more of those, and then that will be chosen. So yeah, you're providing two alternatives, one of which will never fail, one of which could fail, and if the one that could fail succeeds, it will be chosen. Yes?
You said that void t swallows the compiler error. What do you mean by swallows the compiler error?
Well, I'm trying to think of the best way to explain that. I mean, void t, what will happen here is if there's a compile error in here, void t will merely fail to instantiate, which causes this entire thing to fail to instantiate. Okay, and the substitution failure is not an error.
And it has to be as a template argument, not down there where you actually specify the
right.
type.
Yes, it has to be a template argument to make the compiler not actually generate a hard error, because that's the last thing we want. I mean, I tried to do this for some other stuff, with trying things with static asserts and so on, and it's like eventually you wander into a place where the compiler just says, nope, sorry, you're done. You have to actually have something, some template that's going to fail to instantiate. And it's funny because I looked at this once and I said, this is like magic. And then I started working with it, and the more I work with it, the simpler it gets, because it's really not very complicated. But it's brilliant, okay? I wish I'd thought of it myself. I wish I could claim credit for it, because I'd feel real good about myself if I came up with this. And when I came up with something that was about half of this and felt actually reasonably pleased with my cleverness, but this is way better than what I did. And so this, you don't actually see any of this stuff. It's all wrapped up in a header file that you don't even have to look at. These are the things you use. You use detected tells you, did it succeed? DetectedT tells you, or you know, you can use DetectedV if you want, but I mean, DetectedT says, what did I get back? What was the result of that? And in fact, you can also, because detector takes a parameter here which is the default, and if it failed, you get the default type back. Default, none such. You can also just say, you know, you can use DetectedT and test to see if it's none such. That's, you know, if you don't want to actually get a Boolean, you want to test the result. But in any case, I'm going to rewrite a whole bunch of the libc++'s type traits to use this because it's going to make them so much simpler. The only thing I have to worry about is, well, C++03 compatibility, because this all depends on variadic templates. So you have to at least have C++11. All right. Any other questions? Let's see. Yeah. Any other questions? Okay, I'm done. No, just kidding. I have a few more slides. Yes. Many of the slides are examples, but that's okay. So how does it work, right? You provide a type function that takes a type or a series of types and returns a type, and then this applies that and tells you what it is, and yeah, whether or not it worked, and if it did, what the result was. Really simple, really straightforward. No, how does it really work? How does it actually work as opposed to what does it do? And I kind of talked about this, right? We have the two specializations, right? And you have a good one and a bad one, and the good one, if it works, gives you a yes answer, and the bad one always gives you a no answer. But one of the things to take away from this is also this all happens in what's called an unevaluated context, which means there's no code generated. It's all done at compile time. There's no actual variables involved. There's no code generated. And so it's basically, well, basically, you know, we're leveraging, as I said, we're leveraging the compiler's overload resolution mechanism to do work for us, to help us make decisions at compile time about how we want to do things. Okay. Any other questions? All right. Needless to say, this is not just a one trick pony. There are variations on these. Okay, more building blocks that you can do with this. Detected or I had earlier. It says, if you find one of these, great. Otherwise, give me this other type. Remember when I said detected or I had looking for a nested size member versus looking for a, or just using short. Detected or is the mechanism for that. Let's go back to here, yeah. Detected or T, as a matter of fact. Short has size. Use size if it exists, use short otherwise. Again, there's a bunch of places in the standard where it says if such and such type has a nested type, name this, do that, use that, otherwise make something up, usually size T, but in this case I used short. Is detected exact? Gives you the possibility that says, did I do this and what was the type I got back? Was it exactly that? Okay. Is detected convertible, is a little more lenient. It says this type that I got back, is it convertible to some other type? Okay, I got back an int, I was looking for a long, that's fine. You can always convert an int to a long, right? I got back I was looking for a string view, I got back a string. Yeah, I can do that. Things like that. I was looking for an int, I got a complex. Yeah, no, not so much. But I mean, these are all variations on a theme. This one, you know, detected exact. Basically, you look at the return value, the thing that type trait handed back to you, and says, is it what I expect, or is it convertible? questions about this? I'm going way faster than I thought I would. Yes?
Have you got any examples of this coming up? If not, I'll ask the question you have.
Of which? Any?
So, for instance, is detected exact? Like, how would you use that?
Okay. I do have an example for that. So, but basically, let me talk about it for a sec. But you could use is detected exact here to say, does this thing have a size type, and is it exactly size t, as opposed to something else? In this case, if I had yes that was, well, let's go to an example. Okay, variations on a theme. Yeah, hang on to it for like 2 slides. Also, all the examples I've had so far have to do with types, just types, okay? But we're not limited to types. We're limited to working on types because that's a mechanism we have. But sometimes you don't have a type. Sometimes you have a variable. Let's say you are doing something like set, say, and one of your parameters is a function pointer or something like that, or a functor, right, that implements some kind of ordering in the set. And you want to know something about that functor, right? You know what its type signature is, but that's not everything you want to know. You want to know, for example, if it's an object type, does it have a member function that looks like this? Is that member function, maybe you want to know, is that member function a const? Maybe you want to know, is this particular type assignable, and so on. And decal type and decal val, which actually let you walk back and forth between types and instances of a type in unevaluated context without actually generating any code, help out a lot with this. So here's an example. Copy assignment. Okay? We have 3 types up there. Yes, huh, and no. Yes has a very reasonable copy assignment operator. Huh has one that's a little bit odd. Okay? No has one that's deleted. Okay, so we want to say, are these types copy assignable? And so what do we say? I mean, right? What we say is we say, we've got an expression in here, right? On the left-hand side of the expression, we want a tref, and on the right-hand side, we want a tconstref. And we have an equals, an assignment in between them. And we want to say, is this valid code? Is this actually valid code there? And, right, because this happens in an unevaluated context, we don't really want a variable of type t. We just tell the compiler, this thing here, decal val, this is something of type tref, and this is something of type tconstref, and you can go on along your ways without actually making one of these variables. We just want you to do calculations based on that. Okay, and then we wrap it all in decal type because this thing needs a type at the end. Okay, and decal type of that expression. So we're getting the type of the expression. Okay. So if you haven't played with decal type and decal val, this might look very weird to you. But again, it's all in an unevaluated context. And we're just like, I need one of those, and I need one of those, and I'm going to do some operations on them. But I don't actually want any variables. I just want to look at the operations. Okay, so is detected v. Who was asking about is detected v earlier? There's is detected v. So is detected v of copy assign yes? Well, copy assign yes has a very reasonable copy assignment operator. Okay, and it says, oh, of course it does. And huh has an assignment operator that works on a non-const thing and takes a const reference. So it says, sure, right? And no doesn't have one. At which point you say, it's not going to, it's not going to pass at all, hence the bang. But yeah, decal type and decal val basically get you conjure up these things that are going to act as variables if they actually existed, and then not actually perform operations on them, but pretend to perform operations and look at and see if they succeed or not. This is really handy when doing type queries. Okay, questions about this? Okay.
Sorry.
Yes.
Why does the second one here work? I know that this is probably not the best way to write it. I don't understand why this succeeds.
Well, it succeeds because what we're checking for here is we're checking to see that this expression is valid. And something of type you can assign it from a const ref. And that's exactly what this does. The thing that's funny about this is that the return type is void instead of ref. If it was a canonical return assignment operator, would return star ref, or would return ref. So one of the things that you knew, if you tried to actually make things of you couldn't write A equals B equals C equals D, because the first assignment would return a type void, and it'd say, I don't know how to assign a void to a the second one. You couldn't chain them, but this will still do the assignment well if there was actually code there. Yes?
And maybe you should add copy assign in that case, instantiated with as is a type void.
You're getting ahead. You just hang on, Peter. Hang on. I thought I saw another hand over here. No? Okay. Yeah, you're getting ahead of yourself. Okay, so number 2 is detected exact. This says when we do this, right? What is the type that we get back? Because remember, this is the same as before. Everything up to here, from here up, is all the same, right? Copy assign. Because this has to be a type, we wrapped it in decal type, which says, what is the type of this expression? So we did that again. But now what we say is not only is this in fact valid, but the result of this whole thing, which is decal type, is it exactly yes? Is it exactly Is it exactly no? Well, refs, okay? And in this case, yes, because yes has a canonically spelled copy assignment operator. It says you bet. No has no assignment operator. It's deleted. It says no. And in the middle, it says no because the result of this is not a ref, but rather it is void. And so here you can in fact detect that somebody has written their copy assignment operator correctly, or in the normal manner, in the canonical manner. I shouldn't say correctly, because there would be cases where somebody might want to return, not return the reference to the existing object. It would be weird. It's not very common, but it could happen. But if your code depends on being able to, gang assignments together, A equals B equals C equals D, this lets you test that, is this going to actually work? And you see the only difference here, all of this stuff is the same. The only difference is in one case it says, is detected, is the stuff inside here valid, or is this valid? And in the second case it's detected, is it valid and is it the same as that? And so, again, this is why I called these detected exact, detected convertible, and detected or. These are variations on a theme. It's all the same basic underlying mechanism, but lets you get additional information out or check more if you want. And basically you use these, you can use all of these, in parameters to enable if, to to say, I need, here this right here, right? This is something you can reuse, copy assignment. Copy assign, you can use this over and over again. This is basically a function that says, does this thing have an assignment operator, a copy assignment operator, as opposed to a move assignment operator where this would be tref and without the const. And so you can build up a collection of these and use them everywhere, and you just say, is detected exact, say. Enable if is detected exact this. And then you just, as you do this over and over again, you build up a little library of these. Both of these type predicates or type functions, or whatever you want to call them. And yeah, they're type functions. They're not predicates, excuse me, because predicates would return a Boolean value. These always return a type. And then you just start using this in your SFINAE stuff. I have, in libc++, I have lots of very, very complicated SFINAE expressions that I keep itching to rewrite. And every now and then I just look at one and, oh, this is way too complicated. And I define a helper class that does a bunch of this and then use that. And now I can get rid of most of my helper classes too. Yes?
In the second vector map, if you would do the &&, would it be a universal reference or a move construction?
I believe in that case, that would be an R value reference, not a universal reference, and it would turn out to be a move assignment operator. The question was, if I had put tref there instead of tconstref, would that be a universal reference or a move assignment? A forwarding reference, yeah. Pick your terminology. He used universal reference, so did I. But anyway, no, I believe in that case you would be defining an R value reference because it's not in a template parameter list, which is usually where you get the forwarding references or universal references or whatever you want to call it.